In this video, we discuss the Hypercube, which is the basis of many interesting technologies in engineering and computer science. The Hypercube is a recursively defined network. We start out with a single node. In a recursion step, we always double the size of the network. In the first recursion step, we clone our single node. Then we connect the original node and its clone with an edge. To distinguish our two nodes, let's call them node 0 and node 1. Now we can just repeat our recursion as often as we like. For a recursion step, we simply clone the current network by making an exact copy of the network. Then we add additional edges between every original node and its clone. We have to be careful about the names of the nodes though. We want the clones to have different names. Because of this, we add a 0 to the names of all the original nodes, and we add a 1 to the names of the clones, like this. This way we can be sure that all the nodes have a unique name. Every time we clone the whole network, we add a dimension to the network. The original edge and its clone edge are dimension 1 edges, the new edges between the original nodes and the clones are dimension 2 edges. Let's do this again by adding the third dimension. We take our dimension 2 network with 4 nodes and make an exact copy. Then we connect all the original nodes with their clones. These are the dimension 3 edges. Now we can also see why the Hypercube is called Hypercube, since the resulting 3-dimensional Hypercube just looks like a cube. We again add 0 bits to the original node names and 1 bits to the newly cloned node names to distinguish them. The resulting dimension 3 Hypercube looks like this. When we are at a node and follow an edge of dimension d, we end up at the node with the same name, but exactly bit d being flipped. For instance, being at node 111 and following the orange dimension 2 edge, we end up at node 101. Let's remove the node labels to see the Hypercube more clearly. Now let's go for dimension 4. As before, we clone the whole network, and then add new dimension 4 edges. This already looks quite messy, but still follows the same simple principle as before. Next, let us understand some basic properties of the Hypercube. For instance, how far are two nodes apart? The distance between two nodes in a network is defined as the minimum number of hops, as in the number of edges to pass, to get from one node to the other. The diameter of the network is just the largest distance between any two nodes. What's the diameter of a Hypercube of dimension 4? Please pause the video and think about this. Let's try to understand the properties of a Hypercube of dimension d. In our picture, d is equal to 4. First of all, note that a Hypercube of dimension d has exactly 2 to the power of d nodes. We started out with a single node and then doubled the number of nodes with each dimension. So after d dimensions we doubled the network d times, and hence the number of nodes, which is usually denoted by n, is 2 to the d. Each node still has a short node label. With every dimension we added just one more bit, so after d dimensions every node label has exactly d bits. Since n is equal to 2 to the d, a label length of d is exactly log n bits, where the logarithm has base 2. The same is true for the node degree. With each dimension we added one more edge to each node since we put a new edge between each original node and its clone. So after d dimensions, every node has d neighbors. This is also known as the node degree. You can easily verify this in our dimension 4 Hypercube. Every node has exactly degree 4. Now let's answer our question about the diameter. We show that the maximum distance between any two nodes is at most d. Take any two nodes, for instance node 1001 and node 0111. Many paths lead from 1001 to 0111. We already noticed that all direct neighbors of a node essentially have the same name but just one bit flipped. If we want to get from 1001 to 0111, we simply have to flip all the bits for which the source is different from the destination. The nodes 1001 and 0111 do not share many common bits. In fact, only the last bit of the two labels is the same as both end with a 1. The first 3 bits need to be flipped. We can do this in any order, for instance by first flipping the second bit, which means following the dimension 2 edge, then the third bit, and finally the first bit. In a d-dimensional hypercube, we have to flip at most d bits, so to answer the previous question, at most d steps are enough to get from any node to any other node. If all d bits of two nodes are different, the distance between these nodes is d. In other words, the diameter is d. In general, a hypercubic network has many attractive properties. First, we can grow the network to a large number of nodes. These nodes are homogeneous, which means that all nodes are alike, and no node stands out. Each node has a unique short ID, and the IDs span all possible bit strings with log n bits. As we have already discussed, it is also easy to route to any ID. Finally, we want that both node degree and maximum distance between any two nodes should be short, usually logarithmic in the number of nodes. As we have seen, the hypercube naturally has all these properties. But maybe we can do even better. For instance, we might want to have a node degree that does not grow with the dimension, but is bounded by a constant. Let's look at one of the nodes in more detail. The idea is to split up every node in a hypercube into d nodes, one for each dimension, like this. Then we connect the d nodes with a little cycle. We can also give the nodes names to distinguish them, for instance 1.1.1.1, 1.1.1.1.2, and so on. This way every node of the original hypercube is split into d nodes. The resulting network is called cube-connected cycles, or simply CCC. The good news is that every node now has exactly degree 3, but the distance between any two nodes did not get significantly larger. If we want to get from one node to another, we still fix one bit after the other. If we fix the bits in order, say from left to right, we can make sure that we don't have to do many steps in the cycles. In total, the distance is at most 2 times d. One d we spend to fix the bits, the other d we spend traversing the little cycles to get to the next fixable bit. Can we do even better? Assume we want to have a network with n nodes, and all nodes should have a small constant degree, for instance 3. What's the minimum distance we can achieve? Let's start out with a single node. If the network has degree 3, this node can at most be connected to 3 other nodes, so with distance 1 in total we can have a network with at most 4 nodes. If we can have distance 2, we can at most reach 6 more nodes, in total 10. With distance 3, we can reach 12 more nodes, in total 22. Whenever we increase the distance by 1, with degree 3 we can essentially double the number of nodes we can reach. In general, within distance k of our original node, we can reach less than 2 to the power of k plus 2 nodes. In other words, if we want to reach n nodes, we need a distance of roughly log n. Apart from a constant factor, this is exactly what the CCC achieved. Let us summarize the main insights of this video. We have discussed the hypercube network and its close relative, the CCC. Both networks can easily be defined recursively, and they exist in any dimension. Both networks have useful properties. The node IDs span all possible bit strings. We can easily route to any node we like, and the route will be short. Finally, each node only has few neighbors. Thanks for watching this video.